So in this video, we're going to look at some examples of using the geometric distribution. And of course, one of the skills we have to have in the exam is being able to pick it out as a distribution from a question that doesn't tell you. So just to remind you, a geometric distribution, you're looking for a situation where you're asked about the number of trials until one success. If you have more than one success, you're going to need a different distribution, and we're coming on to that. So the geometric is for trials until one success. When you want to write out your model, you have got a variable x, which will represent your trials until success, following a geometric, so we write geo, and then the variable that we've got here is the probability of success, so we just write p in. Don't forget, each distribution that we look at has conditions for use. So we are assuming in this case that our events are independent and that the probability of success remains constant. These can help you pick the distribution, but they're also useful for those comment on the suitability of questions, where these are the sorts of things you could call into question. And indeed, if the thing that you are doing, your trials, are about something where it's reasonable that with practice you would improve, you could argue that your events don't give you a constant probability of success or are in some way dependent on one another. So it's those sorts of things you can talk about. Okay, Bernhard has to pass an exam to get into law school. You take the exam as many times as he likes, and his probability of passing on any one attempt is 0.3. I would be reading something like that and immediately getting a model down. So our x is attempts to pass the exam, and x follows a geometric with a probability of 0.3. The first part is a probability. He needs to pass on his third attempt. So that's the probability that the attempts it takes him to pass is just 3. Well, we know that means he's failed twice and then succeeded. So that gives us a probability of 0.147. Second part, he takes at least 4 attempts to pass. So that's greater than or equal to 4. Now, we didn't talk about this in the last video, but it should be fairly possible to figure out from what we did talk about. So we know that the probability of x greater than or equal to 4, we could write as 1 minus the probability that x is less than or equal to 3. And this less than or equal to formula, we actually have a formula for it. It's 1 minus the probability of failure to the number of attempts. Now you can see that those 1 minuses are going to cancel each other out, which is just the same then as 1 minus p cubed in this case. So you might be able to generalize for a probability that x is greater than or equal to x in this case. It'd be 1 minus p to the power of x minus 1. But it's nice to have the less than or equal to, because that's the way a lot of our other distributions work. So in this case, then that's 0.7 to the power of 3. In essence, we're saying we know for absolute certain he fails 3 times. And then it's he fails 3 times and succeeds the next time, or he fails 4 times and succeeds the time after. And those would add up to a total, leaving you only actually with the certainty that you have, which is that he's failed 3 times, because if it takes him 4 or more to succeed. So that is 0.3430. Part B says, take 2 assumptions you've used in your model. Well, there we go. That's the modelling conditions. So don't forget, with these sorts of questions, they have to be in context. So this would be attempts at the exam are independent, and the second thing would be the probability of passing remains constant. So again, should be a fairly familiar context. It's a fairly intuitive distribution. So hopefully these questions, at least at this stage, feel fairly straightforward. We'll do one more example in this before we move on to another video. So Julian's working in a village pharmacy, and he finds that the long-term average number of customers per hour is 4. That doesn't immediately feel like a geometric distribution. In fact, it should be telling you it's not a distribution, geometric. Running through your other distributions that you should know by now, the long-term average number of customers 4 per hour feels an awful lot like a Poisson distribution. So it's worth noting that these things come into questions with each other. They're not going to necessarily appear in isolation. Okay, so find the probability that at least 5 customers come in during a randomly chosen hour. That's definitely a Poisson distribution question. So we'll define X to be number of customers per hour. Don't forget you do need your time and space frame in that. So we've got our Poisson distribution, it's 4 per hour, and we're asked what's the probability that it's at least 5 customers coming in. Well, that's 1 minus the probability that it's 4 or fewer, and you can work that out on your calculator, 0.3712. The next part of the question then says he records the number of customers during each hour on a particular day. Find the probability that the first occurrence of 5 or more customers is in the 5th hour. And there you go, you get your first occurrence of something. So this is where we get into a geometric distribution. So Y is the first time, perhaps 5 or more customers an hour come in. So Y is going to be a geometric distribution, definitely, and our probability of success is, well, we need to know what's the probability of at least 5 customers coming in any 1 hour, and that is, of course, the probability from the first part. So that would be 0.3712. And then we are asking what's the probability, it's the 5th hour where that happens, so what's the probability that Y is the 5th hour? And that's going to be the first 4 hours don't meet that condition, and then the final hour does. That gives us a probability of 0.0580. Last part, he goes through a whole 8-hour shift with no single hour having 5 or more customers. So that's what's the probability that he goes beyond 8 hours before this thing happens. Well, that's the same as the probability that X is greater than or equal to 9. And from the previous question, we know that that's the probability of failing all 8 times. So we know that the 8 hours he's in, he doesn't see this condition, and that's all we know. But then beyond that point, everything else is going to total up. So this is the only bit that we actually need to worry about. And that gives us a probability of 0.024.